Okay, now that we've had a little bit of introduction to what's inside the Earth, let's get right on to our notes. So there are four major zones that make up the Earth's crust: the oceanic, the continental, and we'll get to the others in a moment. But the oceanic underlies most ocean bottoms. As far as its thickness goes, it's the thinnest of the layers. Up to 5 to 8 kilometers thick. Its composition is mostly basalt. We already talked about that. You guys had memorized the fact that basalt is the most common extrusive igneous rock on the planet. And its density is approximately 3 grams per centimeter cube, or 3 grams per cubic centimeter. Now that's right off of your reference tables. Page 10 has a chart which has that number indicated on there. Continental crust, much, much thicker, 25 to 60 kilometers thick in this case. Mostly granite. Remember, granite is the most popular or common intrusive igneous rock on the planet. And the density, a little bit less, which we talked about before, how the continents are kind of like floating on top of the oceanic crust. And here in your reference tables, they do mention this. There's your density, right there. My pen is not working correct. Let me go back. 2.7 for the granitic crust, 3.0 for the basaltic ocean crust. Just remember they're there. You don't have to memorize the numbers, but they are there to look at. Okay, the mantle. The mantle has three parts. It's found below the crust. The first part is the rigid mantle. This is the uppermost, coolest part of the mantle. And together, the rigid mantle and the crust actually have a separate name, which is kind of confusing. It's called the lithosphere. The asthenosphere, the AKA, also known as the plastic mantle, this is a hotter section of the mantle. It's partially melted. It can actually kind of flow, kind of like a thick tar might flow on a hot day. And beneath that is the stiffer mantle. Stiffer because it's not flowing quite as much as the asthenosphere. This mantle, the temperature is below the melting point, this part of the mantle. So it's not melted. The boundary between the crust and the rigid mantle has a special name in your reference tables. It's called the MOHO, named after the Morohovic discontinuity. I can never say that. And there's the scientists, Andrija, I think that's how you pronounce it, Mohorovic, Croatian geophysicist. There's a stamp in his honor. And he discovered this boundary, looking at seismic waves. So there's the layers of the Earth. In a nutshell, Mohorovic noticed that the speed of seismic waves changed abruptly at this location, right between those layers right there, the rigid mantle and the crust. Okay, getting deeper, the outer core. This is the only liquid layer of the Earth, completely liquid, composed mostly of, we think, liquid iron. And then even deeper than that, it's under so much pressure, so much crushing weight from everything above it, that the inner core, even though it's very hot, the hottest of all the layers, is squished into a solid. And we think mainly iron and nickel, like the meteorites. Speaking of meteorites, the Willamite meteorite in New York City. This is in the Museum of Natural History, in the area where the planetarium is located, the Rose Center, Space Science. And this thing here is a metallic iron meteorite. It weighs over 15 tons. The largest meteorite ever found in the United States. I'm sure there were bigger ones that hit us, but they're not around anymore. And the sixth largest in the world. And you can actually walk up to this thing, and some of my students have actually touched it before on a field trip. And there are those layers, the outer core and the inner core, both we think made of iron and nickel. And off to the right, you can see the densities. 9.9 to 12.2, 12.8 to 13.1, pretty dense layers. So, Earth's interior characteristics. As you go deeper, what happens to density? It increases. Pressure increases. Temperature increases. So these things go up. It's a direct relationship as you go deeper. There's your densities off to the right-hand side. Way up at the crust, 2.7, all the way down to the inner core, 13.1 is the highest. So that's your range. Your pressure, you can see it going from a pressure of relatively almost 0 to up to about 3.6 million atmospheres of pressure at the inner core on the far right-hand side of this graph. And temperature, you can see that near the surface it's pretty much 0, or roughly. And then working your way in, you can see how the temperature climbs very quickly in some places and then kind of gradually in other places. But it tops out around 6,800 degrees, 6,800 degrees. That's in Celsius, and that's at a depth of just over 6,000 kilometers. So the bottom x-axis is depth, y-axis is temperature. And you also notice some melting point lines on there too. We'll get to that in a little bit, but you can see how it says it's above the melting point in some places, and it's above, the temperature is below the melting point in other places. And partial melting too. And we already talked about the convection cells. Just another brief little review of that. Circular movement of Earth's plastic mantle, the asthenosphere. It results in continental drift. And your reference tables represents it in that picture up above where the Mid-Atlantic Ridge is with those arrows. That's how they represent convection. I like the video better, but you get the idea. Asthenosphere. Now we already talked about this, but just remember it's partially liquid, sometimes called plastic. Now this is not the plastic that your pens are made out of or anything. It's another term which means it's flowing very slowly. Kind of liquid but kind of solid at the same time. And another thing that's important to know, where does this heat come from inside the Earth that creates all this convection? Well, we think the best information we have tells us that it's from radioactive minerals that are still decaying inside the Earth, deep within the Earth, giving off heat as they do so. There might also still be some heat left over from the beginning of Earth's formation. Crustal thickness, what you must know. Remember, continental crust is relatively thick compared to oceanic crust. It's made of granite mostly, and it's lower in density. Ocean crust, thinner, made of basalt, and it's more dense. And you'll see in this picture when the ocean crust and the continental crust meet, the ocean crust is always the loser. It gets pushed underneath the continental crust. It gets its revenge later on, you'll see. Okay, inferred properties of Earth's interior review. We're going to do this next time, so I'd like to stop the lesson right here, and let's take a quick review of what we just learned, and then let's move on to another activity.